In this lesson, we introduce the main parameters that identify random variables, and we introduce a few important probability density functions. The main parameters that describe random variables are the mean, that represent the expected average of the random variable, and the variance. The variance measures the dispersion of the random variable around the mean. The greater the variance, the greater the dispersion of the random variables. The square root of the variance is the so-called standard deviation, and it is indicated as sigma underscore x, where the variance is sigma underscore x squared. Both average, mean value, and variance can be computed through a specific operator that is the expected value function. That is a specific operation, a specific operator that is defined in this way in the case that we have a function of the random variable x. The expected value of the function of the random variable x is the integral of the function of the random variable times multiplied the probability density function. And if m is a number, then the expected value of m is the number itself, because there is not a random variable. Since the expected value is a linear operator, you see it is an integral, the sum of the expected value of the sum of two random variables is the sum of the expected values. And in general, it's not true that the expected value of the product of the two random variables is the product of the two expected values. Let's start from the computation of the mean value of random variables. You see that the mean variable is the mean value, is the expected value of the random variable itself, and it is computed as the integral of a, since the function is just x, you see, times the probability density function integrated in dA from minus infinity to plus infinity. The variance is computed as the expected value of x minus the mean all squared, that is computed as this integral here. But usually the variance is computed by using the mean square value. In fact, if we develop this square here into the expected value, we found x squared minus 2x mx plus mx squared. And since this expected value is a linear operator, we have the expected value of x squared, that is the mean square value, plus the expected value of mx squared, that is mx squared itself, is a number, minus 2 times x mx. 2 mx can be extracted from the expected value, and we have, again, the expected value of x, that is mx. So we have plus mx squared minus 2 times mx squared, and so in total we have the mean square value minus mx squared. Let's see some example. First of all, let us consider a uniform probability density function. Uniform probability density function means that the density function is a constant in an interval from a to b, and of course the amplitude of this probability density function is 1 divided by b minus a, divided by the interval here. Remember that the integral of a probability density function is always 1. And the mean value that is computed in this way is just the value in between in the mean of a and b, a plus b divided by 2. And this is the case in always the case when we have a symmetry of the probability density function. If we have a point of symmetry, of x of symmetry, the probability density function, that is the mean value of our random variable. The computation of the variance of the uniform probability density function goes through this, the computation of this integral here. And here it is important to remember the particular results we get in this case, because it's quite simple to have it in mind, because the variance of the uniform random variables is just delta squared divided by 12, where delta is the interval b minus a. So if we have these uniform random variables from a to b, so the interval is b minus a, delta, the variance of this random variable is just delta squared, the interval squared, divided by 12. And this is the expression of the mean square value of the random variable. Another very important random variable probability density function is the Gaussian or normal probability density function. Why is this so important? Because in the real world, many processes, many phenomena are described, are modeled as a Gaussian random variable, because thanks to the central limit theorem, it is shown that if we have many independent random variables, regardless of their distribution function, the sum of these independent random variables is a Gaussian random variables. That's why many natural events can be described, are described as a Gaussian random variables. This is the expression of the Gaussian random variables. You see that it is in an explicit way shown the mean and the variance. And this function here is just a bell-shaped function centered around the mean, mx, and the variance, sigma square of x, is responsible of the width of the bell. The larger is the variance, the wider is the bell of the Gaussian random variable. Well, in this case, it is important here to have an idea of the probability that are below the Gaussian random variable. And as a matter of fact, almost all the probability, almost 99%, is included into the values of A that goes from the mean plus 3 times sigma to minus mx minus 3 times sigma. So mx plus minus 3 times sigma includes almost all the probability of the Gaussian random variable. Another important random variable is the exponential one. The exponential random variable models the time between successive events in the Poisson process. What is a Poisson process? In a Poisson process, we have events that occur continuously and independently at a constant average rate lambda. We have a number of events per unit time that is lambda. And this is the probability density function that models, remember, the time between successive of this type of events, where you see one parameter is lambda, that is the average rate of the events. The mean value is 1 over lambda, and the variance is 1 over lambda square. This is one important probability density function widely used in many processes, especially in the communication theory. This is the shape of the exponential probability density function, just to give you an idea of the position of the mean with respect to the curve that descends exponentially here. Another important probability density function is the Rayleigh random variables. It is quite widely used when we have to compute the absolute value of a complex random variables where both a real and imaginary part are Gaussian, independent, zero mean with the same variance sigma square. And the shape of this Rayleigh probability density function is this one. The mean, as this form over here, depends on the standard deviation of the Gaussian variables v and z, and the variance of the Rayleigh depends again on the square, that is, on the variance of the variables v and z. Quite important function, widely used in physics and engineering problems. If you are not interested into the absolute value, but we are interested into the square of the absolute value, so we remove the square root here, and we get this random variable here, v squared plus z squared, where v and z are independent random variables with Gaussian probability, zero mean, same variance, sigma square. Well, we get back to the exponential random variables. That is, this probability density function of this random variable x here is again exponential, where lambda, that was, you remember, the occurrence rate of Poisson events, is now 1 over 2 over sigma square. The shape is again the same of the exponential here. The mean value is 2 times the variance of the two variables v and z, and the variance of x is 4 times the square of the variance of v and z. There are other parameters that are used to describe a random variable. One is the mode, that is the most probable value of the random variable. It is not widely used in physics and in communication processing. The other parameter, that is the median, is widely used because the median represents the value for which there is a 50% of probability of obtaining a lower value and 50% probability of obtaining a higher value than this median value. Why it is important? Because it is an alternative centrality parameters to the mean that is more resistant to outliers. So imagine you want to identify the mean, the central value of your random variables, and you have a process, you have a random variables who have numbers coming from an experiment that are affected by outliers, a few values that are outside the statistics of your problem. Well, the median value is much more robust than the mean value in order to identify the centrality, the central value of your random variable. Just to give you an idea of the difference between mean, median, and mode of a probability density function, look at this function here, probability density function, that is linear from -2 to +1. The mean of this probability density function is 0. The mode is the value 1 that corresponds to a in correspondence of the highest value of the probability density function. And the median here is computed as the value here in the red circle here that allows us to get half the probability of our probability density function. And this value here is a value between 0 and 0.5, so different from the mean of our probability density function.